Hello, everyone. Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be going over some past paper questions that focus specifically on finding empirical and molecular formulas. So this particular question is from the Cape Chemistry, Unit 1, Paper 2, and this was from June 2005. Okay, so this is question 7, part C. And it reads that two isomeric compounds, A and B, containing only carbon, hydrogen, and oxygen, are subjected to combustion analysis. 1 gram of each compound, so that's our isomeric compound, on complete combustion gives 2.3 grams of carbon dioxide and 0.93 grams of water. The relative molecular mass of each compound is 58. So we're being asked to calculate the empirical and molecular formula of A and B. Now, because A and B are isomers, it's important to note right away that they will have the same molecular and empirical formulas, okay? Remember, isomers have the same molecular formula, but different structural formula. So the way that we draw them would be different, but they have the same molecular formula. And so whatever molecular formulas and empirical formula we get for A, it's also the same for B, okay? All right, so let's get into this question now. Here is how we're going to approach it. So let's get started here. All right, so here's what we're gonna do. We're going to just write out a generic equation which represents the combustion of each of these isomers A and B. So they told us right off the bat that we actually have in compound A and B, it's comprised of carbon, hydrogen, and oxygen only, right? So that's what our compound looks like. We don't know how many carbons, so we can just use X to denote the number of carbons that would be there in that formula. And we could use Y to denote how many hydrogen should be there, and then Z to denote how many oxygen should be in that molecular formula ultimately, right? So this shell of a formula represents our molecular formula of A and B, right? That's going to get combusted per the question with oxygen. Oxygen is our agent of combustion, right? And of course, it could be a gas phase isomer as well. And then we would get our carbon dioxide and water. Of course, those are our products of combustion. So we have CO2 gas being formed and water. Okay, steam rather. All right, so here we are now. So let's write all the information that they gave us. They told us that we would, as a result of this combustion of these isomer compounds, we would have gotten, well, first of all, we would be combusting 1 gram of each. And as a result of that combustion, we would get 2.3 grams of carbon dioxide and 0.93 grams of water. Now, the important thing I want to point out here is that whenever we write a balanced equation, the stoichiometry really means from this part that this is the molecular formula, right? However, that whatever we find here, so any X, Y, and Z that we would find from this balanced equation, if we were to balance by putting numbers here, would be the molecular formula, because we write molecular formulas in our balance equation. That's what our balance equations are comprised of. However, because we're being asked to find the empirical formula first, which is an experimental formula, right? We're gonna just look at the experimental amounts of each isomer that we combusted, which is 1.0 grams of it, and we were able to form 2.3 grams of carbon dioxide and water. So what we're gonna do is the first thing we're going to think about is that, okay, remember the law of conservation of mass, right? So if I am getting 2.3 grams of carbon dioxide, what that means is that all of the mass or all of the grams of carbon that was present in the original compound is going to end up in the carbon dioxide, because these carbons all are going to end up here. And similarly, the hydrogens that end up here in the 0.93 grams of steam that we get all have to originate from over here, right? And similarly for the oxygen, well, the oxygen is a little bit more interesting, right? Because we have oxygen here and oxygen here, and the oxygen is coming from the combustion agent here, so this molecular oxygen, and it's also coming from the compound itself. So that's a little bit trickier how we would treat that, but let's get into it and see what we have so far. Okay, so ultimately what we're trying to find, right, is the amount of carbon present in the 2.3 grams of carbon dioxide. From an empirical formula standpoint, that's what we're seeking, right? And similarly, we are trying to find also, because it's an empirical formula, we are trying to also find the amount of hydrogen present in 0.93 grams of water. Okay, so that's what we're seeking from an empirical formula standpoint. So what we're going to do now is we're going to say, okay, if we look at 1 mole of carbon dioxide, right, in a molecule of carbon dioxide, it's made up of 1 carbon, which has a mass of 12 grams. So we're going to say there would be 12 grams of carbon present in the whole molecule, which has a mass of 44 grams. Right? So that's the fraction of carbon that we have in every molecule of carbon dioxide. And since we only have 2.3 grams of carbon dioxide, we can multiply that fraction by 2.3 grams to find out how much carbon do we actually have in this sample here, okay? And it turns out that that number is 0.6272 grams of carbon, okay? So that's how many, that's the mass of carbon that we were able to get from this combustion. And so it follows then that that mass of carbon that we got must have came from the compound itself, the isomeric compounds that we combusted, okay? All right. So let's do the same thing for hydrogen. If we take a look at 1 molecule of water, we see that there are 2 hydrogens in there. And each of them, they have an atomic mass of 1. So we're going to say 2 times 1 is the fraction of hydrogen in 1 molecule of water, which has a mass of 18 grams. Okay? And so because the mass that we were told that we got from the combustion is 0.93 grams, we're going to just multiply that by 0.93 grams to find out then what was the mass of hydrogen in that sample. So again, we do the same thing. Grams cancel gram from over here, and it's the same thing here. That gram goes with that gram, and we're left with the mass of the sample there. And it turns out that that number is 0.1033 grams of hydrogen. Okay? Again, if it is that we're ending up with 0.1033 grams of hydrogen in this sample, it means that they all came from over here, right? Okay, so what remains now is we want to find, so what we now know, right, is that in this 1.0 gram sample that we burned, right? So let's write that down here. In the 1.0 gram sample of A and B that was burnt, there was 0.6272 grams of carbon and 0.1033 grams of hydrogen, right? And so if the question they told us that that sample was comprised of carbon, hydrogen, oxygen only, if we know the mass of the carbon and the hydrogen that was in that 1 gram sample, then we automatically know how much oxygen was in that from a mass perspective as well. So to find out, what are we going to do? We're going to say that then the mass of oxygen in the 1 gram sample, right, would have been 1.0 grams minus the sum of the carbon and the hydrogen. So that would have been 0.6272 grams plus the 0.1033 grams from the hydrogen. And so that would turn out to be that the mass of oxygen that was in this 1 gram sample was 0.2693 grams. Okay? All right. So now we have a plethora of information that we can use. So here's what we're going to do now. This is really our starting point to really, be able to then go from a mass of elements present to an empirical formula. Okay, so now we're ready to work. So what I'm going to do is I'm going to just erase this portion, and we'll go from this text box here. So let's do that. So we're going to just take out this preliminary work that we did here. Right? We're just going to take this out for now, just to give ourselves some more space. So we don't need this anymore. We're just going to bring this up now, okay? All right. So that's what we're starting with. So it's essentially what we have now from an empirical standpoint, right, is that we have, for carbon, we have that is 0.6272 grams. For hydrogen in our original sample, right, that 1 gram sample, we had 0.1033 grams. And then oxygen now, we just calculated that we would have had 0.2693 grams. And so what do we do when we have these masses now? The masses of the compounds that were the masses of each element that was present in that compound that we combusted, we're going to divide them through, right, by their molar masses to get the number of moles of them. By molar masses to get moles. All right, so that's our next step. So when we do that, what are we going to do effectively? We're going to be dividing the carbon by 12 grams per mole, because that's the molar mass of carbon. We're going to be dividing the hydrogen by 1 gram per mole, since that's the molar mass of hydrogen. We're going to be dividing the oxygen by 16 grams per mole, since that's the molar mass of an oxygen atom. Okay? When we do that, we're going to get moles of carbon to be 0.05227 moles, right? For hydrogen, this is going to come out to 0.1033 moles, right? And for oxygen, this is going to come out to 0.01683 moles. Okay, so once we've gotten these number of moles, since it's an empirical formula, we have to divide by the lowest number of moles, right? That's our next step. Divide by the lowest number of moles to get the simplest whole number ratio, which is what our empirical formula is, right? And so when we look at these three numbers here, the smallest number, or the lowest number of moles, is this one here. And so we're going to divide through all the moles that we got in this step by this number. So let's start by dividing the carbon moles by that. So that would be 0.01683 that we're dividing the number of moles of carbon that we had gotten by. And that will end up getting 3.1 in this instant, which we can just round down to 3. When we divide the number of hydrogen, moles of hydrogen, by the smallest number, we're going to do that, right? And then we would have gotten there that the simplest whole number that we can get there is actually 6.14. And so if we round that down, we would get 6 being our whole number, right? Similarly, for oxygen, it was the lowest number of moles, so we divide it by itself, right? Which is that same 0.01683 moles. And when we do that, we end up with 1. Okay? So then our final step now is to put it all together. Put it all together. And so when we do that, we're going to put the 3 beside the C because that's how many carbons there are. There are 3 carbon atoms in the simplest whole number ratio. There are 6 hydrogen atoms rather, and then there are 1 oxygen. There's 1 oxygen atom. So this is our empirical formula. Okay? This is our empirical formula. Now, the next step that we're going to do now is that they're asking us to come up with a molecular formula. And this is now our starting point, right? From the empirical formula. And they gave us the relative molecular mass of the isomers. They said that that's 58. So what we're going to do now is we're just going to clear out all the work that we did to get the empirical formula. And then just put that as our starting point, okay? So let's get rid of all of this work that we did here. Very important work. And then bring up our empirical formula, or we can just rewrite it up here so that we have it. So the empirical formula, right? We just found that to be C3H6O. So if we want to find our molecular formula, the first thing that we want to do is write the formula really, or how we're going to connect the molecular formula to the empirical formula. And the formula that we had discussed in our previous lessons was that the empirical formula times a factor n is going to give us our molecular formula. And so we have to figure out what n is, right? So n we can find by dividing our molecular formula mass, right, by our empirical formula mass. We know that the molecular formula mass is 58 because they gave us that, so we can just drop that here for now. And we can calculate our empirical formula mass by simply adding up the molar masses of these elements that make up this compound here. So to do that, we would simply do 3 times 12 for the carbon, right? The carbon portion of that molecule. And then we would do 6 times 1 for the hydrogens to account for all the hydrogens. And then we would add 16 for the 1 oxygen that's present. And when we do that, right, we have our 58 from the top. And then when we add this, we're essentially adding 36 plus 6, which is 42. And then 42 and 16 is 58. So we find out that the empirical formula mass and the molecular formula mass, or the molar mass, is the same. And so n is just simply 1 in this case. So if we come down here now to apply our formula here, our empirical formula was C3H6O. We're going to multiply that by n, which we found to be 1. And would you look at that? our molecular formula is exactly the same as our empirical formula. Okay? So that's our answer. So our molecular formula and our empirical formula are exactly the same. Okay? So there we go. That's our molecular formula. And this is our empirical formula. And they're exactly the same in this instance. Okay? And remember, this formula that we just got for both our empirical and molecular formula applies for both A and B because they're isomers of each other. Okay? And so just to recap what we did here, we first found the empirical formula, right, using the law of conservation of mass. And then from there, we were able to relate the empirical formula to our molecular formula. And so we ended up with our final answer down here, okay? And it turns out that the empirical formula and the molecular formula were exactly the same in this instant. So definitely give this video a like. Definitely subscribe to our channel and turn on the notification bell so that you'll be first to know when we add more practice questions and also more content, okay?